All right, so 3.2 is going to be types of bonding. So we know that elements can combine, and that's all well and good, but we want to talk about how they combine and the different types of substances that they can form. So we're going to first talk about ionic compounds. So to give a simple definition, ionic compounds are compounds that are made of metals and nonmetals. And if you look in the periodic table, the bulk of the elements there are metals. So everything to the left of the stair-step line, which you'll notice is near like aluminum and boron and silicon, everything to the left of there is a metal. So we define it as a metal. Everything to the right of there is a nonmetal. So if you combine something from the left with something from the right, then you have what we call an ionic compound. These form from the transfer of electrons. So one element has too many electrons, one doesn't have enough, so there's a transfer, and that transfer allows those two particular elements to satisfy their outer shell of valence electrons. We'll draw orbital diagrams to show this later on. The compounds exist in lattices. I'll show you what a lattice looks like in class tomorrow, but in essence, it's like an alternating box that has different elements at the vertices of that box, and I've got a couple of models to show you in class tomorrow. The ratio of the elements in the lattice give us the formula. So for instance, when we say CuCl2 or copper 2 chloride, that refers to 1 copper ion for every 2 chloride ions. 1 copper for every 2. So it's not like we just have 1 copper and 2 chlorines, we have a ratio, 1 copper for every 2 chlorines. Traditionally, these things have really super high melting points, very difficult to melt them. That's because the bond between the ions is really, really strong. So there's very high what we call electrostatic attractions. Electrostatic is just the attraction between one element and the other, or one ion and the other. Oh, and look at there. There's a picture of the lattice that I was referring to. So each one of the green spheres is representing one element, and it's a little bit difficult to see, but the orange spheres are representing a second element. And in this case, we've got a 2, 4, 6, actually a 6-to-1 ratio. So this might be something like sulfur hexafluoride. It's going to be ionic. Sorry about that. So it's a 6-to-1 ratio for this particular substance in a lattice structure. This is kind of what they look like. They form little crystals when they're in the solid form. All right, covalent compounds. These are a second type of compound. Molecular or covalent compounds in general don't conduct electricity. These things are composed of non-metallic elements. So in the U-tube experiment, we actually tested water. We tested deionized water. And the deionized water did not conduct electricity. And because of that, that's one of the reasons that tells us that the water itself is a covalent compound. When these molecular solids are dissolved or melted, they break into neutral molecules. So molecules, individual molecules by themselves. And these things usually have lower melting points because they have low electrostatic attractions. So here I've got a sugar molecule. Okay, and I can break that apart just by adding a little bit of heat. And so we get the two individual molecules. Those individual molecules are neutral. So one thing that you do not have with a covalent compound is the formation of an ion. All right, and then lastly, metallic bonds. Oh, my pumpkin's in the way. Sorry about that, everybody. Metals, that's that word right there, metals. Metals gain their structure using metallic bonding. Okay, and what is metallic bonding? Well, the valence electrons of the large groups of atoms are shared between all the atoms. So I kind of think of this, if you look at the image down here in the lower right-hand corner, I always like to think of metallic bonding as like little bugs swimming in a pool. And so the pool water is denoted by the positive things down there. Those are the metals. And the little bugs are the electrons. Those are the red things. And they're just kind of swimming around all willy-nilly. And so they're moving back and forth and back and forth and back and forth and back and forth. That's kind of my idea or my thought process when I think about metallic bonds. All right. So we could also say it's like a sea of electrons, which helps to explain why metals are such good conductors. Because if we think about it, what does it mean to be a conductor? It means to be able to pass electricity through, or to be able to move electrons. And in this case, what are we doing? Well, we're moving electrons. We're passing electricity through the metal. We can actually form things that are not pure metals. We can use the properties of two different metals or two different substances, and we can combine those two things and make something really super special called an alloy. Okay, so an alloy is just simply defined as a metal made by combining two or more metallic elements. And you are very familiar with a whole slew of different types of alloys. The first one I'll talk about is steel. Steel is not an element, it's not on the periodic table, but what it is a combination of iron atoms and carbon atoms. Most of it's iron, but the carbon comes in to do two things. It reduces the weight of the particular material, and it increases the strength. Steel is stronger than iron, and it's less massive. Really important when you're building things. So how does that look? Well, essentially, if I got a blue dot for every iron atom that I have in my alloy, and then I'll change that and I'll make a green dot for every carbon atom I have. And so the carbon atoms are kind of just displayed or dispersed throughout the iron atoms to reduce mass, but increase strength. The other alloy I wanted to talk about real quickly is stainless steel. Stainless steel happens to have an extra element incorporated with it, and that's chromium. And the chromium actually acts as a surface barrier that prevents rust. So what happens when things rust is, or in the case of iron or steel, is that oxygen atoms actually can interact and chemically combine with the iron, forming iron oxide. This decreases the strength of the material, it makes it crumble apart, and it doesn't look good. And so what we do is we cover that material with a thin layer of chromium, and the chromium acts as a protection barrier. That's stainless steel. All right, so the question might arise, how do we know the ratio that elements combine with, like H2O? How do we know that? Or in the previous example, I had copper 2 chloride, CuCl2. Well, it's all got something to do with oxidation numbers. So the oxidation number is the number of the charge an element would gain if it were to become stable. So let's go ahead and take a look at a little chart right here with a whole bunch of different elements on it. We've got lithium all the way down for neon. We're going to start at the bottom of the chart. Neon isn't going to want to gain any electrons, right? No, not at all, because it's perfectly full in the outer shell. So neon has an oxidation number of 0. Now, what about fluorine? Fluorine, look at that. Look at how close it is to being stable. It needs just one more electron. And when it gains that one more electron, it's going to have an oxidation number of 1 negative. Oxygen is going to be 2 negative because it needs 2 electrons in order to become stable right over here. Again, to fill up that shell. I think you're seeing a pattern, right? Nitrogen, 3 negative. Carbon's interesting. Carbon's really interesting because here's what it can do. It can either gain 4 or it can lose these 4. And so carbon's oxidation number is either 4 positive or negative. Boron's on the other side of the ladder, so it's going to want to lose all 3 of these that I'm boxing in right here. So if it loses, it's kind of weird, right? It's going to be positive. Why is it positive? It's got 3 more positives now than it does negatives if it loses those electrons. Beryllium's going to lose 2, so 2 plus. And finally, lithium will lose just that 1, so 1 plus. Okay? So those are the oxidation numbers for those particular elements. And guess what, folks? If we take a look at a periodic table, we can see a new trend. Where's lithium? On the far left, right? And we said that the charge on lithium is 1 plus. Beryllium is 2 plus. Boron is 3 plus. Carbon, 4 plus or minus. Nitrogen, 3 minus. Oxygen, 2 minus. Fluorine, 1 minus. And helium is 0. That's a minus on fluorine, by the way. All right, and so what I'm trying to show you is the oxidation number, the 1 plus that we had for lithium, is the same oxidation number for all the elements there in the column. Oh, look at that. So now if I said, what's the oxidation number for potassium? You would be really super smart, and you would say, oh, Mr. Koenig, it is 1 plus because it's in that column right there. All right. Now notice we did skip the transition metals because they're kind of weird, and we'll get back to them a little bit later. But what I would encourage you to do is take out your periodic table and write above them the oxidation numbers for these particular columns. Again, these are the numbers or the charge that the element would want to gain if it were to become completely happy. All right, that's bonding.